This is a walkthrough slash lecture for the homework tides in Miss Volkening's physics class. So this is kind of these were the exact questions we answered in class. So this will be a little bit abbreviated because I want to keep this under 10 minutes. But we're gonna use these basically as Cornell notes. These are the questions. Then we're gonna do the answers on the right hand side, like we were taking notes. So anyways, what causes the tides on Earth? So it's the moon, but not just the moon, but the gravity of the moon. And we're going to talk about the sun in a little bit too. Basically what's going on here is you've got the Earth. Let's see the Earth here. Here we go. This is totally not going to be to scale, you guys. Oops. No. Okay. Not to scale at all. Please keep that in mind at all times. Alright. So we've got the Earth. And I want you to think of the Earth as basically a layer of water over a rocky surface. Okay, let's just pretend that that's what it is. Okay, so I've got this layer of water, and then we're going to use green for rock, because I don't know why. Anyway, okay, that's the Earth. And then you got the moon over here. Again, not to scale at all. Okay, moon. This is not to scale at all, like not even close. Okay. Here's the thing. As we learned earlier, gravity actually pulls harder on things that are closer than things that are far away. So that means if you look at points on the Earth, like this point and this point, and I need another color, lavender, this point, the pink point gets pulled harder by the moon than any of the other points. So what you got is it's being pulled the hardest. The orange would be pulled second most hardest, okay? And the lavender is pulled the least, but still pulled, okay? This is not to say that it doesn't get pulled at all, but ooh, you can't see that, can you? Let's thicker arrow. I still can't see it. There's an arrow there, okay. Now, I don't know if you've ever had a tug of war with a friend of yours, and when I say with a friend of yours, I mean that your friend of yours is the one being tugged. But if you're pulled harder on one side than the other, you get a bit stretched. And in fact, that's what happens to the Earth. It actually happens to the whole Earth. The whole Earth gets stretched a little bit, so you get kind of a bulging out on this side, but water moves a lot easier than land, so although the land does bulge out, and it's like, I don't know, 6 inches or something, nobody notices. For one thing, it's over a huge area. But people do notice that the water tends to bulge out over here. So the water tends to bulge out on this side. Totally not to scale. I think I've said that several times, but I just want to make really clear about that. Okay? So you get this kind of bulge over here. Now on the other side, because the lavender is pulled less than the orange, it's kind of like, well, you know, an object at rest tends to stay at rest unless acted on by an outside force, a net force. What we kind of get here is the water is not pulled as hard as the land, so the water's kind of stays there with its inertia. It just kind of, it's a little bit left behind. So we have it stretched out on this side too. So there's actually two bulges here. There we go. Okay, there's actually two bulges. And then what happens is the Earth spins. So I didn't show this, but basically, like, oh, let's go black. Black. Here's the axis. The Earth then proceeds to spin around on its axis, you know, like it does. And if you're standing, say, here, you're at high tide, and then the thing spins around, and on the other side you'll be at low tide, and then it spins around, and you're at high tide again, and it spins around, and you're at low tide again, and it comes around, and you're at high tide again. So in one spin, which is one day, that's what we call a day, you're going to be at high tide twice, and at low tide twice. Okay? So when we come over here, what causes tides on Earth? We're going to say the moon's gravity does it. Moon's gravity. Gravity, okay? How many high tides are there per day? Well, there's two, because the moon pulls harder on the near side. I'm just going to put on near side, and causes a bulge. Wow, I'm having trouble writing. Causes a bulge. It pulls least, how about least, on far side, leaving a bulge behind. That's kind of simplistic, but that's basically what's going on. Okay. Now, it says, what is a spring tide? When does it occur? What causes it? A spring tide does not occur in the spring. Well, it does, but it occurs other times too. Spring tide is basically what happens when the Earth and the Moon and the Sun make a line, because we didn't talk about the Sun yet, but the Sun has gravity. I mean, it better, or else we'd fly away in a straight line. It actually has, it's much, much, much larger than the Moon, but it's also much, much further away, and distance is what really matters with gravity. So although the Sun pulls harder on the Earth than the Moon, the difference of the Sun's pull on each side is less, because we're so far away that this distance, the width of the Earth, doesn't matter so much. So what we got is, if we have Earth, and actually I'll do Earth as blue. If we have Earth and Moon and Sun, I'm gonna put the Sun here. Sun. If the Earth, the Moon, and the Sun line up, what we get is the Moon causes tides on the Earth. The Sun also causes tides, but they're not as big or significant. But they're there. They're like, geez, I'm not even sure. I heard like a quarter the size of the Moon's. But if they're all lined up, then the Moon causes bulges, the Sun causes bulges. Basically, the Moon's and the Sun's bulges line up, and you get really, really big bulges. So what we get is they line up, and we get really, really big tides. Really high tides, really low tides. Okay, so what is a spring tide? That is really high tides and really low tides. Okay? What causes it is that the Sun and Moon's tides basically add up. They add together. When does it occur? Now here's the thing. I need this line to happen. So this happens when the Moon is on the far side of the Earth from the Sun. That's a full moon. That's when you get the Sun shining on this side of the Moon, and the Moon reflects that side, shiny side, back to us, and we see the shiny side. That would be the full moon. Okay, come here. It's a full moon. Okay, because this is basically this side's lit up. That'd be a full moon. Okay, so it happens at a full moon. But you also get a line if the moon is here. Now keep in mind, not to scale at all. So this is when this side's lit up. Lavender isn't really lit up, but we're pretending. And we can't see that at all because we're over here. So that's a new moon. New moon. Okay? So basically, this spring tide happens twice a month, and it does. Spring tides are good for if you want to get something up high on the beach, because that's when you're going to be highest, and then it won't come up that high again for a while. Okay, let's look at the back. What is a neap tide? When does it occur? What causes it? This is a lot like a spring tide, except for it's exactly the opposite. So let's put the Sun here. Sun, Earth. Okay, so what this is exactly the opposite. This is one you're going to have the Sun, the Earth, and the Moon kind of in a, I guess this is not a good picture, sorry. It's kind of in a, like a kind of a right angle kind of a thing. Because what you get then is the Moon is trying to make bulges here and here, but the Sun is trying to make bulges here and here. So the Sun kind of undoes some of the Moon's work, which means you're still gonna get high and low tides. The Moon wins, okay? The moon wins. But you're gonna get lower high tides and higher low tides. Okay? Good for when you don't want the water to come up as high on the beach. What causes it? This is the Sun's tides subtract. Sun's tides subtract from the Moon's tides. When does it occur? Well, when it's lined up like this, and again, not to scale, basically this side is lit, but we only see this, so it's half lit from our perspective. That is, hang on, I have to think about that for a second. That is first quarter. Oops, not that. Oh my god, that is supposed to be a Q, not a G. Quarter. Okay, first quarter. Oh my god, I did it again. Wow. Sorry, I'm rushing a little bit because Downton Abbey starts in like 5 minutes and I need to get out there to my living room and watch it. Okay, but I can also get the same arrangement if the moon is over here. In which case, this side is lit, but I see this side still half full, but now that's a third quarter right there. Third quarter, getting really sloppy now. Sorry. Downton Abbey, people, come on. Third quarter. That's when it happens. Okay, why is it a bad idea to try and enter a black hole? What would happen to you and why? Well, you die. Yeah, but that's not the answer I'm looking for. A black hole is nothing more than a collapsed star. Now, a star with a lot of gravity. All stars have a lot of gravity. A black hole has no more gravity than a collapsed star, but the thing about a black hole is it's very, very compact. So you can get a lot closer to it than you used to be able to. Because the star used to be like, well, this big, you know? It used to come all the way out to here. And so you couldn't get any closer than that because then you'd be inside the star. You can't get closer than the star. So by collapsing, it freed up all this space. So if you went into a black hole, let's say you did a little, I don't know, a dive. I don't know why you'd be diving in, but let's just pretend you would. As you get closer, the difference in the pull on the part of your body closest and the part of your body that's farthest away, it would get different amounts, just like before with the moon pulling on the Earth. Okay? It's just that now you're close enough that the gravity difference is big enough that the length of your own body is enough to have a different amount of pull. So like the top of your body might be pulled a certain amount and the bottom of your body might be pulled a lot less. And if you're being pulled less or different amounts on both sides, eventually that pull will exceed your structural integrity of your body and you're going to get cut in half. You know what? I should just use an eraser for that. There. Cut in half. Well, that's not cool. I mean, that's going to kill you. But it gets even worse. I mean, you're still being pulled toward the black hole, so you're going to get closer. And as you get closer, another picture, just same guy, but now we've got little pieces of him. Ah, that's so sad. Okay, as you get even closer, the smaller and smaller differences would result in a gravity gradient that was enough to rip you. So not only would you be ripped in half, but as you got closer, you would be pulled. Okay, they should be in the same direction and it should be toward the black hole, but I'm just being sloppy because Downton Abbey, people! Downton Abbey! Okay, anyways. You get cut in half again, that's my point. Okay, and that would continue to happen until you were nothing but a stream of atoms stretched out, falling into the black hole. The point is you'd be dead. You'd be dead because your top of your body gets pulled harder than the bottom, and you'd rip. Okay, so that's what I'm looking for. You'd rip because the closer part of your body is pulled harder by gravity than the further part. Okay, and that concludes Worksheet Tide, Town for Downton Abbey.